Okay, so now let's take a look at something very interesting. So it's some problem that I had for quite some time, right? So let's try to implement a procedure that copies a chunk of memory, right? So let's implement MEM Copy, something that we call MEM Copy in the industry. So this is going to be MEM Copy. It's not really Porth, right? It's rather Porth. There we go. So this is going to be something like this. So we're going to include, I think I already have MEM Copy in the standard library. So let's actually not include it then. Okay. MEM Copy is going to accept 3 arguments. It is going to accept the size of the memory chunk that you need to copy. Then it's going to accept the source, right? The source of this thing, and then the destination, right? So it's going to copy the memory from here to here. So, implementing such procedure without any local variables is kind of difficult, actually. Knowing, like, having all of the operations that you have, all of the intrinsics to work with stacks, like duplicate, swap, and so on and so forth, it's kind of difficult to juggle 3 arguments simultaneously. So the way I actually implemented that is I allocated a bunch of variables, right? So I basically offloaded these two variables to a separate memory. So we're going to have MEM Copy src, right? And since both of these things are pointers, we're going to provide the size of the pointer, right? So it's going to be something like this. And this is going to be DST. So both of them are size of the pointer. Since we don't have the standard library, I'll have to define a constant myself, size of PTR, and the size of the thing is going to be 8. There we go. Right. And the first thing I want to do, I want to actually save the arguments into that thing. So it's going to be 64. Right, so we take the destination and then we save in this thing in here, then we take the source, we save in this thing in here, and after that, on the stack, we're going to have only the size. So we sort of like simplified this stack a little bit for us by offloading the arguments to the memory, right? So after that, we should be able to quite easily iterate like n times, or rather size times. So we're going to define a loop while duplicate is greater than 0. We're going to keep looping, and we're going to be subtracting. We're going to be subtracting 1 from the current index. All right. After that, I need to grab the source, right? So that gives me the pointer. I read that pointer. So it gives me the value that I will probably have to cast to the pointer, and then I read the character. There we go. So basically, I read the first character from the source, and then I go and grab the destination. I read the value of the destination. I cast it to the pointer, and I'm writing the red character into here. Right, I'm writing this character into here, and after that, I can just go ahead and increment the source by 1 and the destination by 1. Right, so, and after that, we only have the 0 at the top of the stack, and I can just straight up drop it, and there we go, we implemented MEM Copy. Right, we implemented MEM Copy, but there's a huge problem in here. Right, it uses this global memory region, which actually pollutes the namespace, right? It pollutes the namespace, and on top of that, it's like not part of the stack. It's not like a local variables. So clearly, you kind of need local variables to comfortably develop functions that accept a lot of arguments, right? So, and the question is, how can we do that? Well, as far as I know, recently I learned that Porth allows you to use not only the data stack, but also the return stack. So here's an interesting thing. In fact, in both Porth and Porth, there are 2 stacks. The first one is a data stack, and the second one is the return stack, which stores the return addresses every time you call a procedure, right? Every time you do a MEM CPY, we push the next address after MEM CPY to the return stack, and then we jump in here, execute, and when we reach the end, we jump back to the address that is in return stack. So Porth actually decided to allow the programmer to push values on the return stack. Right. So as far as I know, like Porth return stack, right? So return stack, it has special intrinsics that allow you to basically exchange the values between the data stack and the return stack. So, and because of that, you can use the return stack as the location for the local variables, right? So essentially in Porth, you would just push src and dst to the return stack, then you will keep iterating, bringing src and dst from the return stack, modifying them and pushing them back to just increment the size and until you like finish the entire thing. So, which is actually pretty cool idea, and but I had a slightly different idea. I was thinking, what if we go ahead and allow the programmer to define the memory locations inside of the procedure? It is possible right now. You can define memory locations inside of the procedures. But what if you do that? It actually makes them local, and it allocates them not in the global BSS section, but on the return stack. And then once you return, whatever memory you allocated on the return stack is going to be automatically cleaned up. So it basically implements local memory regions. So, and that way we can also make it so in terms of the namespaces, we can get rid of the prefixes and actually, make them local to that specific procedure. Right. To that specific procedure. There we go. So, yeah. It's kind of similar to the like pushing values on the return stack. It's just like you have a little bit more control of the things that you can put on the return stack. As far as I know, in Porth, you can only push the values of the size of the word on the return stack, which is kind of understandable, I suppose, because Porth works in a very weird embedded architectures, maybe where you could have some weird memory access limitations, and maybe because of that, like you want to restrict the size of the things you can push on that stack. But I don't think we're going to encounter such situations, so why not allow this kind of thing? And in the future, once we have the variables, right, so you're literally going to have like a local variables of a particular type, which are allocated on the return stack, and it just like basically behaves like local variables and shit. Yeah, so I think that's pretty cool. So, and I'm thinking, implementing the ability to push values on the return stack is actually super easy, and will kind of temporarily solve the problem with local variables for now, right? But having local memory regions is a little bit more complicated, but yet I think it's a little bit more convenient to use because you have specific names associated with the region memories, memory regions, right? So you have a specific value called src, specific like name called dst, and it's just like overall a little bit easier to work with. So, and I'm thinking, so which one I want to do? Do I want to do the Porth way, or do I want to do, the mainstream way? Because this is more like a mainstream local variables. So I'm thinking, and I kind of want to try the local memory regions way. I think it's going to be kind of cool. Shouldn't be really difficult to implement. It may require introducing a bunch of operations to the intermediate representation, right? So we definitely will need to introduce a new operation that allocates a size, like a chunk of a memory of a particular size on this stack. So it's going to be new opcode in the intermediate representation, and accessing, like pushing the pointer to that region is also going to be a separate opcode, because the regular opcode that pushes the memory, it actually pushes it relative to the global memory. So for the local one, you'll have to generate a little bit more code that retrieves the current position of the stack, the current size of the stack, and calculates the things, and only then pushes the pointer on the stack. So we'll need to introduce at least 2 new opcodes to the intermediate representation. With the operations that push values on the return stack, we only will need to introduce like 2 intrinsics, which is kind of the same, which is also kind of introducing new opcodes, because each individual intrinsic is basically like allocated space in the opcode space. So yeah, I think these kind of solutions are equivalent in terms of the difficulty of implementation. I think they're kind of like equivalent in terms of difficulty. And because of that, I want to try to go the local memory region route. So, and that way, by the way, we're gonna have like a proper like stack things, and it will make it like easier to have recursion, right? Though we have a little bit of a problem with recursion. Tab checking doesn't really work with the recursion right now. But anyway, so let's go ahead and try to implement local memory regions. How about that? How about that? So I'm going to try to go ahead and compile this entire thing. So we have a MEM Copy example, right? It's going to be porth.py, and I'm going to compile memcpy.porth, and it doesn't know about increment 64. Okay, so I already have a MEM Copy in the standard library. So if I just include the standard library, it's not going to compile. So I probably want to rename memcpy to something else, right? I want to rename this thing to something else. Let's actually call it MEM Copy. Right, MEM Copy, and see if we can compile this entire thing. And it compiled. It successfully compiled because you are allowed to define memory regions inside of the procedures. It's just like they're going to be global, right? So this entire thing is going to become global. Right, one of the things you want to do in here is just go to the compiler, right, and change the way we parse things. So porth.py, so parse program, and if we encounter memory, right, if we encounter memory, in here we may always check whether we are inside of the proc or outside of the proc, right, because we keep track of that, literally, we keep track of that. So we have a variable called current proc, right, current proc, and it's optional, so it can be none. None means you're defining globally, but if it has an operation address, that means you're currently inside of the procedure, right? You're currently inside of the procedure, and this is the way we can actually check for that, right? So we define the memory, and we can assert that current procedure is none. So local memory regions are not supported. There we go, and I'm going to try to compile this entire thing, and as you can see, here we go, we hit that assertion. So, and if I move this entire thing outside of the procedure, it will perfectly compile. So as you can see, we can easily detect whether we have a memory outside of the procedure or inside of the procedure. That's pretty straightforward. Cool. So, and if we have the memory inside of the procedure, right, so we have to do this kind of stuff slightly differently. Maybe. It's actually very interesting. So we probably want to do keep doing the same thing. We still want to parse the name. We still want to parse the location. Check for the word. Well, checking for the word definition is going to be kind of interesting. So we also want to maybe pre-evaluate the size, right? And only somewhere around here we want to distinguish whether it's a local memory word or a global one. You see what I'm talking about? Like only then we wanna try to do that. Okay, so here's the current proc. Here's the current proc. If the current proc is none, we check for the redefinition as usual, and we just add global memory addresses, right? So these are global memory addresses. Otherwise, we're going to do assert false to do local memory regions are not implemented yet, right? They are not implemented yet, and they are in fact not implemented yet. So how are we going to approach this entire stuff? So we may try to extend the procedure, right? So we may try to extend the procedure. So in the procedure, we have an address, operation address, where this entire thing is, located in the program, and location in the source code. We may try to introduce something like memories, right? So here are the memories. And the memory could be just a dictionary, right, that maps a particular name. It maps a particular name to, I suppose, memory of set as well, right? It could be also memory of set since the beginning of the frame, I suppose, right? Since the beginning of the frame. Maybe we can just go ahead and just put a memory in here. So these are local memories. We might as well call them local memories, literally. Right, and if we are current proc, right? So if we are current proc, we may wanna add the memory not to like the global space, but rather to the local space of the procedure. Right, but we don't have the current procedure because the procedure is actually created afterwards, once we reach the end. Right, and the current procedure, current proc, does not point at the current procedure object, it points only at op address, which makes it kind of inconvenient in my opinion. So I think current proc has to be not optional OP address, it has to be optional procedure. See what I'm talking about? Okay. So, and let's run the type checking, right? So it's gonna be my py, and let's go through all of the type checking stuff. So current proc, if the current proc is that, we are assigning this IP. So maybe I want to do something like a proc. Is it address? I think it is address. So this is gonna be class. It is in fact address. So here's a proc IP. So we also have a token lock, proc location, which is basically like token location, but I'm not really sure. So we're already redefining a token in here, which is fine, I guess. So maybe we're gonna put this thing in here, right? So it's gonna be token, yeah, proc lock, proc name, check for the redefinition, and only then we define proc, proc name, and so on and so forth. But this is only for the, oh boy, this is only for the for the end, isn't it? This is only for the end. So we're redefining it like that. Just a proc name. Okay, so I see what needs to be done. So we need to also do current proc, proc name. So we want to actually keep track of the pointer to that specific procedure. Right, to the pointer of that specific procedure. So let's go ahead and recompile it one more time. So missing positional, and then we're gonna have local memories, and this entire thing is gonna be, so local memories is the dictionary, so it's gonna be like empty one. Okay, cool. Unsupported operand types plus for these kind of things. So the current proc. So I suppose it has to be more of a proc address. Yeah, it has to be more of a proc address. Anything else? No overload variant for this thing. Proc address. So we need a proc address in here, which is rather interesting. So maybe... I see. So we'll have to use current proc address. But since we have the location, we can just collapse this entire thing into just that. Right. So we can just take a current proc location. We know that it's not none, and that should be fine. Anything else? Okay, so that's fine. Okay, that's cool. That is very, very cool. Stack append, preparation of our nation, and everything seems to be okie dokie karaoke. Now let's go ahead and try to run this one more time, right? So we are gonna run it one more time. And now we should be able to add the memory region to the local memories, right? So we should be able to do that relatively well. So we're gonna check for the word redefinition, right? We're checking for the word redefinition, and interestingly enough, we want to be able to redefine all of these words. Okay, so maybe I'm gonna just basically do the same thing, but instead of memories, I'm gonna use the current proc memories. Okay, so because we want to be able to allow the local memory regions to redefine the global ones. Do we? Do we want to be able to do that? I think so, actually, if you think about that. So they basically will shadow them. So the local memory regions should be able to shadow the global ones. Oh, maybe not. I actually don't know. Maybe. Should they allow to shadow that? Should they allow to shadow that? So what is easier to implement? I think it is easier to implement right now to allow them to shadow that. So maybe that's precisely what I'm gonna do. And maybe later we're gonna, disallow that, who knows. So this is gonna be to do. So local memory regions can shadow the global ones. The question is that something we actually want? So that's a good question. Is that something we actually want? I have no idea. Okay, so we have memory capacity in here, and so in a global way, we just keep track of the global program memory capacity. In case of a procedure, we want to keep track of the of its local memory capacity. I think so, and this is going to be actually very useful because it will let us know how much we'll have to deallocate at the end of the procedure, right? So when we reach the end of the procedure, we'll have to deallocate everything that was allocated on the stack, and since we keep track of the capacity of this entire thing, we kind of know what to do, right? So that makes sense to me. That kind of makes sense to me. Okay, so that means I need to go to proc. So here is local memories, and here's the local memory capacity, right? So it's going to be an integer. Local memory capacity, and in here we want to do procs. Actually, current proc, right? So here is the current proc. Current proc memories, right? Current proc memories, memory name, memory name. So memories, memory name, and I want to create a new memory with offset equal to the current procedure, local memory capacity. Local memory capacity, and location, it's a memory location, right? So this is going to be memory location, local memory capacity. And then what we have to do, we probably have to increment current procedure, local memory capacity plus memory size. Achilleos77, thank you so much for tier 1 subscription. Thank you, and welcome to our epic Porth club. Thank you, really appreciate that. All right, so what do we have in here? So it complains about local memory capacity does not exist somewhere. Missing one, oh yeah, it's missing one of them. Okay, so local memories and then local memory capacity, right? So it's going to be equal to 0. There we go. Procs doesn't have memories, but this is because it has local memories, right? So this is the local variables memories. And another mistake in here. There we go. Unknown word DST. Okay, so perfect. This is actually very cool because it's allocated. Look. It complains about unknown word DST. So it defined this thing in here, but now this thing is unknown, right? This thing is straight up unknown, which is actually very cool. Okay, now what I can do, unknown word. So here, as you can see, I check if something is defined, and if the current procedure is not none, so that means you are inside of some sort of current procedure, and token value is in current procedure memory, local memories, you are referring to the local memory. So we can quite easily catch the moment when you're trying to refer to a local memory inside of the procedure. You see what I'm talking about, right? So, and we can do something like assert false, referring to local memories. Memories is not implemented yet, right? So this one is going to be to do. There we go. Okay, and we actually hit that. To do. Cool. So now when you are referring to the local variable, we have to push a new intrinsic. So in case of a memory, we just push mem, right? But in case of this one, we have to push local mem, I suppose, right? So we need to do something like push local mem. Program ops append op type push local mem, right? So it's going to be token equal token operand, and this is going to be current procedure, local memories, token value, and we're going to be using the current of set. So there we go, and that's going to be just IP+1. So, but this is only one intrinsic. There should be another intrinsic to allocate the memory. And I think it should be at the end of the procedure definition, right? Once you define it, a new procedure, we should have like a local memory, right? Yeah, I think this is what we have to do. Okay, so let's go ahead and define some new operations. So we're going to have a push local memory, right? So this is going to be one thing. And another thing we need to have is maybe a local memory, right? So these are the two operands that we need to have. What is going on in the chat? Okay, so I don't know what the fuck is going on in the chat, but you guys need to calm down. All right, so let's continue. Let's continue. Okay. Mods, if we have any mods, anyone who using that command, 1 hour timeout. Okay, so let's continue. So this is going to be that exhaustive OP handling. So we added 2 of them. So it's going to be 16 and then 17. All right. So this is the type checking, by the way, right? So we'll need to do some sort of a type checking. But I think type checking for this thing is all right, right? Because it's not going to do anything special. So it's going to be OP type push local memory, right? So in that case, we're going to do stack append, right? Stack append data type pointer, OP token, right? OP token, then we're going to increment the IP of this entire thing. So in case of the alloc, I don't think we need to do anything with the alloc. So op type alloc local mem. So and I think we're just not going to do anything here, right? Because it's just like doesn't need to be type checked, right? Doesn't need to be type checked. All right. So did I update this thing? Okay, I didn't. So 16, 17 push memory. All right. So elif op type push local memory, and this is going to be assert false not implemented. op type alloc local memory. So yeah. Okay, so we hit not implemented. And this is where we should start doing the entire thing. The question is, how are we going to do all of that? That's a very good question. So let me see. Maybe we want to draw something. I also want to open the window because it's a little bit hot in here. It's a little bit hot in here. So we have the stack, right? We have the stack, and so the stack grows towards the zero, right? So it grows towards the zero. So here is the stack. Here is the stack. So when we perform the call, we actually push the return address on the stack. So the stack is located in here. Every time we allocate a little bit, right? We allocate a little bit on the stack. We need to keep track of where the top of the stack is located. That's a very actually interesting thing. So we already store the top of the stack in the return stack RSP, red stack. This is actually super cool, right? We already store that, which means that we can just update that value to point in here, right? We're gonna update it to point in here, and since we know this offset, right? We know this offset, we can quite easily just like figure it out. So, and if we do that several times, how do we know how much we have to subtract at the end? Well, this is precisely why we kept track of the local memory capacity. Because that local memory capacity is precisely the size you have to subtract before trying to reach for the return address. This is actually pretty cool. So everything is working out perfectly. So we have all the necessary information to actually allocate the memory, figure out the addresses of the local memories, and we also know how much we at the end have to deallocate. So that's actually super. Well, it's not 100% true actually. Fuck. Because you might be, we might be allocating some memories. We might be allocating some memories in. Well, you know what? You know what? We can pre-allocate all of that memory. So my concern was, chat, my concern was, what if you have some sort of a condition here? So if false, like some sort of a test, if test, you allocate a little bit more, right? You allocate a little bit more. So what's gonna happen in here, right? So if this test is always false, this thing is never going to be allocated, so we cannot just subtract the whole capacity that we just accumulated, right? So we cannot just subtract the whole capacity. So we need to keep track of the allocated memory dynamically. But another interesting thing, as we compile, we actually accumulate all of the sizes of all of the possibly allocated memories. We might as well just pre-allocate the whole thing on the stack at once, regardless of whether you're going to reach that thing or not, which will simplify the implementation. Of course, it's going to be wasteful. We do a lot of wasteful thing in our compile already. We'll do a lot of wasteful thing, but this is because we are experimenting, right? We're trying to get to a particular point as quickly as possible. So what I'm trying to always find right now is the easiest thing to implement. So the easiest thing to implement right now would be to get rid of the alloc local memory and just pre-allocate the whole memory capacity at once. The whole memory capacity at once. So, and that will make everything fucking easier. That will make everything easier. Figuring out the offsets is gonna make it easier. Yeah, everything is gonna be easier. So yeah. All right, so let's go ahead and do that. So that's actually really cool. Okay, so maybe I'm already streaming for almost 2 hours, and when I stream for too long, I get really tired super quickly. So yeah, maybe I want to make a small break. Maybe I want to make a small break super quick, and after this small break I'm gonna continue, and we'll see how it will go. So all right, so let's go ahead and implement what I want you to implement. So I don't think we need a local memory, right? Because we're gonna pre-allocate all of the local memories in the prep procedure, right? So pre-allocating everything that is needed is going to be part of the preparation of the preambula. I think the original name for this thing is a preambula or something. I don't 100% remember. So yeah, let's go ahead and do that. So we have this thing. So alloc. We don't even need that. Everything starts to make sense, actually. I really like that. Everything starts to make sense. So we push local memory, and it's just going to be offset from the RSP and stuff like that. I love that, actually. I really like that. Though it's unclear how we're going to be doing that in a simulation, so we'll see how it goes. But for now, we only need like 16 of this stuff. So here is 17, and this one is going to be more of a 16. So allocate local memory, and maybe in here I want to prep procedure, and I want to do assert false. But the question is, where are we going to be storing all of that? Right, where are we going to store? We might as well make the size that you're supposed to allocate part of the operand of the prep proc. That is actually a very good idea. So this is how we're going to do that. So a p operand, right, is instance of the integer, right? So this thing has to be the size of the local memory that you have to pre-allocate. Okay, so, and this thing already failed the assertion, which is good. So op type prep proc. So let's find the place where we push this entire thing. Right, we're preparing the procedure, and once we are preparing the procedure, oh fuck, shit. So do we push anything on the stack, though? Do we push anything on the stack? I really don't think so. Right, so we kind of need to push prep proc on the stack as well. Because then I want to go back to the prep proc and just do something about it. So here is a skip procedure, and then we append this entire thing, and maybe here we can try to do that. Why not? So let's actually just append this entire thing. Right, so because we'll need to come back to both of these operations, we'll need to come back to both of them, and for the prep proc we'll have to set the memory that we have to pre-allocate, like a local memory, and for the skip proc we have to set the place where it have to go to skip the entire procedure, right? So that's what we have to do in here. So let's try to recompile, and we're already failing. So and can only close procs. Okay, so that makes sense. So let me find this place, right? Let me find this place, and that will. Okay, cool. So we have a skip procedure. Where is the skip proc? Okay, that's cool. So here's the skip proc. And as you can see here, we're setting everything up. So I suppose what I have to do now is program ops block IP type. I need to check that it's a type prep procedure. Prep proc. So this is a prep proc. And in here, what I have to do? Do we have? Oh boy. Yeah. So we have to append. We don't really have to append anything yet, but we have to go back to the original thing, and as an operand, we have to set current proc local memory capacity. There we go. So the operand of the preparation becomes the local memory capacity. That's what it becomes. So let me actually also put assert false in here. To do not finished, because I want this thing to fail. So this thing is not finished yet. And I also want to go to the place where we handle the procedure preparation. So this is a simulation, so we'll probably have to also put a false in here, because we'll have to pre-allocate some memory there. We'll have to pre-allocate some memory, so we'll need to allocate some memory for the local storage and whatnot. So to do not implemented yet, so we have to be super careful. So this is the type checking. In case of a type checking, I didn't think I need to do anything in here. And in here, this thing is not finished yet, right? To do not finished yet. It's really easy to forget to add something. It's super easy to forget to add something. That's why I put like as many asserts as possible, so I don't forget to go to these places eventually and implement some things. So yeah, so it's sort of like I leave some sort of stoppers and markers for myself to not forget to add things there, because we're dealing with a very complex system, actually, relatively complex system. I'm pretty sure there are way more complex systems, but this thing is relatively complex. Right, and it's quite easy to forget to add something and then spend a lot of time like troubleshooting and whatnot. Okay, so especially in such a dynamic language. Okay, so we have not finished and we are currently in parsing. Right, so we have that. So that is very, very POG. That is very, very POG. The next thing I probably want to do, I want to sort of like pop. I want to pop yet another block, and I know that after that, that block IP must be skip procedure. So I'm going to even assert that. So it must be skip procedure, otherwise we made a mistake somewhere there. And only then, I might as well actually remove this entire stuff. Okay, so I just sort of circumvented that. So you have a preparation, so for the preparation you put that thing in there, then you pop another one, expecting the skip proc, and for the skip proc you just add another thing in here and just clean up the current procedure. Okay, so that makes sense. That makes sense. So what else do we need in here? And there we go. We are in a generation. So this is like, I already anticipated that I will need to go in here. All right, so procedure preparation, I get the RSP, and I save it in there. That's very, very interesting. But before I go and save RSP in there, I think what I want to do is I want to subtract Holy shit, it starts to feel like the code that is generated by compilers such as GCC or Clang, right? So because they usually quite often just subtract something for RSP, pre-allocating some, like a little bit of memory. And the thing we're gonna allocate there is located in the operand, right? So the operand contains the amount of memory we have to pre-allocate in there. Look at that. That's beautiful. So yeah, that's perfect. And then in the return, we also kind of know how much we have to deallocate. Or not. It depends. So return doesn't know how much it needs to deallocate. So let's actually put a stopper here as well. So this is going to be assert false to do. Red does not know how much to deallocate. Yeah, it doesn't know how much to deallocate, and we're gonna probably pass the amount of it needs to deallocate via the operand. So we'll have to do is instance op operand integer. No awesome comment for call and return. I forgot to put them in there. So to be fair, these kind of comments are not particularly useful. What I'm thinking is that maybe I'm gonna actually do a very dumb thing. Out right 1 2 3 4 right, so something like S and just like I don't know, OP type, right? Or maybe just straight up OP, right? Because I keep forgetting these comments. I'm not sure if they're that useful. So yeah, maybe I want to get rid of them completely. So I didn't think it's that important. So so another one. Well, I mean, yeah, whatever. So this is the end. So I just recorded a macro for Emacs to just find the next comment and remove it. So I can just go and just delete them automatically like that. I think that's pretty convenient. So for things like this, we might do something like if operand is in one of those things, right? Cast like so and boolean. We're gonna just do pass, right? And then we're gonna continue. So yeah, macros in text editors are like a must to have in my opinion, right? Because they allow you to just quickly do this kind of stuff. And the comment that I just generated in here is probably going to be horrendous. I'm pretty sure about that because it's just like gonna take the whole thing and just generate some crappy shit in there, but I guess that's fine. I guess it's fine for now. So what do we have in here? We have an else. In case of a while, we're gonna just put a pass in there. Right, so and what do we have in here? So this one has to be something like this. There we go. So red does not know how much to deallocate. That's a good point. And as you can see, it doesn't have any operand set up. So OP type return. So here is the OP type return. And we usually do that in a prep. Oh shit! That is actually very fucking cool. So essentially, yeah, we can set operand as the same thing in here. As the same thing. There we go. So now it does know how to do that. Oh shit, we actually missed this thing. Okay, so here's the RSP. We sort of recovered the RSP. And I suppose what we have to do in here is outright add RSP D OP operand. Right, so that's what we want to do here, I think. We might as well take a look at the assembly that got generated right now, because I'm kind of curious. Right, so yes, that's what I was talking about. maybe it's fine. I guess, I mean, it's just like assembly doesn't care, right? So it just doesn't really care, but at least we have like a lot of information of what the fuck is going on here. And we even have like the text, the location, the actual values, like we have literally everything. So might as well actually keep it in here, why not? So, yeah. So I want to find something like return, and I found the return. So yeah, everything looks okay. Add 0 because we never actually allocated anything in there. That's fine. Look, you can optimize this thing. You can actually optimize this thing. Dr. Poopy says, yo. Thank you so much for 7 months of Twitch Prime subscription. Thank you, and welcome to our epic Porth Club. Okay, so now we need to push a local memory. How are we gonna push a local memory? That's a good question. So I wonder what I can do in here. I'm gonna take out right, and I'm gonna move rex return stack RSP. We can use return stack RSP as the beginning of the local memory. That's what we can use. So we move this pointer to rex, then since we know the offset, we're gonna add that offset to the rex. We're adding that offset to the rex OP operand. So here we need to also assert that this entire thing is OP operand, is a memory address, of course, right? And after that, we should be able to push rex onto the data stack, giving the program the pointer to the return stack memory. That is very fucking poggers. That is in fact very fucking poggers, isn't it? I think it is. So, and it compiles. This shit, by the way, compiles. We have no way to properly, you know, verify that or check that. But yeah, how can we do that? So having local memory should allow us to implement something like toSwap. Who knows what is a toSwap? toSwap. So toSwap accepts 4 values and swaps the pairs of them, right? So essentially it's going to be something like this. Yeah. And if you have a local memory, you should be able to implement toSwap not as an intrinsic, but actually as a procedure. And this is something that we can actually observe and CDAB. Okay, sorry. So let's go ahead and implement that and see. So toSwap Porth. Proc toSwap. So A, B, C, D. So how many things we want to allocate in here? I'm not even sure. So, so we need to achieve CDAB somehow. Yeah, maybe it would be easier to actually do something like this. So we're gonna have a memory A, size of U60. We might as well actually do something like this: A, B, C, and D. Right, and then I can do D, 64, C, D, C, B, A. And after that, I should be able to do the following thing. So it's going to be C, 64, D, 64, B, 64, A, 64, and then just end. It's kind of a dumb way of implementing that, but it's just to test things around, right? You see? Okay, 1, 2, 3, 4, toSwap, print, 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 print. Okay. Actually, let's comment it out and see the output of this entire thing like this. So this is going to be compile R to swap. Okay, so 4, 3, 2, 1. If I do to swap 1, 2, 4, 3, we have local variables. And the question is, can I access those things like here? I cannot. They're truly local. If I try to access A, it will say unknown word. Right, so you can only access those things within the procedure, so you can have local variables. That's pretty cool. Oh, you can just allocate a bunch of memory on the return stack. You can just allocate a bunch of memory on the return stack and use it as a local storage. And when you go out of the scope of the procedure, all of that local storage is automatically deallocated. You don't have to think about that. B and A are swapped. Maybe, I'm not sure. So D, C, B, B, A. Then I guess it has to be like 3, 4, 1, 2, right? Well, 1, 2, 1, 2. It might be, maybe it's something like that. Is that what it has to be? It's kind of confusing, but you get the idea. So it's just like, I suppose if it's a mistake in my implementation, not in the local storage, right? So if I understand correctly, probably, I don't know. So what I would expect this thing to produce 1, 2, 3, 4, 1, 2. So the result has to be 2, 1, 4, 3. That's what we expect, right? 2, 1, 4, 3. 2, 1, 4, 3. So probably, oh, it has to be like literally CDAB, like so, right? 2, 1, 4, 3. Okay, so we got it right. 2, 1, 4, 3. We did it. So we have a CDAB. How about that? I'm actually super fucking happy. So that will make implementing procedures with a lot of arguments a little bit easier, because then you'll be able to offload some of the arguments to the local memory, right? You're offloading some of the arguments to the local memory, and for the rest of the arguments, you just work them on the stack or something like that. We can finally probably implement the recursive Fibonacci number calculator. So let's actually give me a try. So right now we have a little bit of a problem with type checking recursive functions. So let me see. So this is going to be n, right? In case of the n be in 0 or 1, so it has to be less or equal to 1, right? If this thing is less or equal than 1, that means we just return that. If it's not less or equal than that, right? It's more of a like if it's greater than 1, what we'll have to do. Memory A, which is going to be that, and B. So in here, what I'm going to do, I'm gonna duplicate and subtract 1 and call Fibonacci with that, and then I'm gonna save that result to A. Right, I'm saving the result of that call to A. Then I'm duplicating this entire thing and subtracting actually 1. I'm calling and saving all of that to B. So after that, after that, I want to drop this entire thing and just take A, B plus, and otherwise in here, yeah, that's actually fine. So this is the Fibonacci number calculator, I think. Right, because if n is less or equal than 1, n is the result of the Fibonacci number process calculation. You see what I mean? Otherwise, we just store intermediate values into like local like stack. So that way we can have like a proper recursion that can utilize the stack of the call stack. Right, so now we can do something like this. Dupe less than 10. Maybe less than 10, right? And in here I can do dupe fib print. There we go. So on each fib, it will just recursively compute that. So for 0, it's going to be 0, 1, and so on and so forth. So let me see. Unknown word A. Okay, so I'm sorry, it has to be something like 64. I forgot that I haven't implemented that syntax yet. Unhandled data on the stack, and this is because I forgot to drop that. And there we go. So here's the problem with the current type checking. The current type checking doesn't know how to check the recursive functions. So it basically hangs. Right. So I'm going to fix that later. It's not really that much of a priority. But basically, if you have something recursive, just do that with unsafe. And this entire thing actually also hangs because I forgot to increment the counter. Right. So there we go. Okay. Does it look like a Fibonacci number sequence? Does it look like a Fibonacci number sequence? I think it does. I think it does look like a Fibonacci number sequence. So the only problem here right now we have is the type checker not being able to properly type check the recursive procedures. But if you do unsafe, you can have like a proper recursion due to having local memory regions. So yeah. I think this is actually super cool. This is actually super cool. So I have constants, I have local memory storage, and I think that should be enough to implement everything I want to implement. Though, yeah, I need to still somehow being able to type check the recursion. So one way I can see we can implement the type checking is by implementing proper signatures for the procedures, if you know what I mean. Right, so basically we need somehow to annotate that this thing accepts one number and returns another number, so the type checker doesn't have to go recursively into the calls to check everything, right? It can just go here, and since it knows what accepted and what's returned, it can just check that and stop the whole recursion. So right now, since we don't have such information, the type checker actually goes inside of the functions and just type checks like literally everything. It just almost like evaluates the program, making sure like there's no like stack of underflow or incompatible types or whatnot. So yep, that is actually very cool. So I'm gonna use this thing as a test for the stuff maybe. So does anyone have any questions maybe? Does anyone have any questions about today's stream? So we implemented local memory storage, and now you would be able to actually allocate something on the local stack. How do you return from procs? What do you mean by that? You mean, yeah, when the execution reaches the end, you return from the procedure. This resembles how you'd implement the actual intrinsic, and I like it. Yeah, it's kind of cool that it almost looks like a proper programming language, which is disgusting. Should have actually just implementing an ability to push things on the return value, like in Porth, and just have the language look like this. Because obviously this is more elitist and cooler than this. This is too fucking readable. Like, seriously, this is too fucking readable for normies. It has to look like this. But I'm a normie, so what can I say? Would implementing type checking for recursion require a double pass? No. Don't think so. If you want to return 2 or more values. Oh, you're talking about returning values. You said, how do you return from a function? Returning from a function, you just reach the end and you return from the function. If you want to return 2 values from a function, it's a separate question that has nothing to do with the previous one. If you want to return 2 values from a procedure, you just return 2 values from the procedure. Yep. There we go. You can return 4 if you want to. It all works. It even type checks, by the way. Okay. Well, almost. Not enough arguments. So this has to be 16. Yeah, there we go. Not enough arguments for the print. You see? The type checker went inside of the toSwap. It observed that it returns 4 arguments on the stack. Then it sees that you have 4 prints, but it sees that you also have the 5th one, but you don't have enough arguments for the 5th one. And all of that happens before you actually evaluate things, right? So you can have something like include std porth, right? Include std porth, side effect. So you put some sort of a side effect, right? And if you try to compile this entire thing, as you can see, the side effect was not evaluated in any way. So there's no side effect in here. So there's no execution. But then you do that, and here is your side effect. And then this entire thing, our type checker actually checks this kind of stuff. Yep. And in the future, we don't have any type signatures because of that. And because of that, the type checker actually goes inside and like literally checks everything. But as we introduce like type signatures, we'll be able to say that this thing just transforms the stack in a particular way, right? So maybe we'll be able to say something like, I don't know, toSwap is supposed to be like thing that swaps to like pairs of the arguments. So it's going to be int, and it returns int, right? And then the type checker will take this information. It will know that this function consumes 4 elements, 4 integers from the stack and returns 4 integers on the stack or something like that. I mean, whatever. So we'll see how it goes. I don't know. I'm not sure about the specific syntax. I don't care about specific syntax. For some reason, people care too much about language syntaxes, and I really don't understand why. Because syntax is literally the easiest thing to change in a language. Like you just like go to the parser and you just change it. The thing that are difficult are the semantics, right? Because a slight change in the semantic may result in a huge change in implementation. Like you slightly change something and all of a sudden you need a second stack and then you need some pre-calculation before you go into the function and just like shit goes crazy. So it's really difficult stuff and it actually affects how you can use your language and on what architectures you can use your language. Syntax is literally like nothing. It affects almost nothing. I don't know why people are so wind up about syntax. Like it's literally insane. It's just really strange to me. Because syntax is the easiest thing to implement in a language and modify and change and experiment with. It's like, it's just a cover. It's just like, yeah, you change it, but the language stays the same. I don't know how sorting is getting function signatures. The secret is I don't. There is no function signatures. That's the secret. And that's why I was talking about implementing them. Because I want you to have them. But right now, I don't have function signatures. Because syntax is the most obvious. I suppose it's literally bike shedding. Nafli, you're right. It's literally bike shedding. So people just have an opinion on things that are easy to have opinion on. It is difficult to have an opinion on implementation of it is hard to have an opinion on implementation of like local variables, but it's easy to have an opinion on a specific keyword in your language, right? Because it's whatever. And people always look at superficial parts first, yeah, I guess. Okay. So we need to do a committee, I suppose, and maybe even pushy. You know what I forgot, by the way? You know what I forgot? I forgot to check the simulation. I forgot that we live in a simulation. That's what I forgot. All right, so we have that, and okay. So 1, 2, 3, 4, to swap, print. Okay, so, and we have something like this. So now I should be able to use this stuff, in tests, right? To swap, and I'm gonna just move this entire thing in there. So, and if I try to run tests to swap for the simulation, right? So this is that. So we're gonna have 16. So push memory, and we have to do push local memory. OP type push local memory, right? Assert false. Not implemented. Right. Not implemented. Okay, so this one is rather interesting. How are we gonna even approach that? We need a chunk for a local memory. I mean, it's actually kind of not that interesting. So essentially I'll have to allocate some memory for the byte array in here and then just use that memory. It's like, it's pretty straightforward. So I think I'm going to leave it as a to-do. For now. So push local, was it push? Yeah, it was a push local mem. Oh, this is the type. Not implemented. Prep, also not implemented. So that makes sense. And yeah, this one is also not going to be implemented. Rote intrinsic can also be proc now. Yeah, a lot of things can be proc now, actually, if you think about it. Right. So maybe this kind of thing will allow us to significantly reduce the amount of intrinsics. Actually, if you think about it. Because you just need to implement the way to allocate local memory, access the memory, and deallocate local memory, and the rest of the stuff is going to be just expressed in terms of that. Yeah, that's actually a pretty cool idea. All right, so I guess that's it for today. Thanks everyone who's watching me right now. I really appreciate that. Thank you for all of the subscriptions and beats and stuff like that. I really appreciate that too. I'm gonna finish it off after the stream. Have a good one, and I see you next time. And next time, I don't know what we're gonna do next time. I think so far we have everything we need. We have everything we need to continue implementing the self-hosted compiler. But I don't know. So basically, when I said that I have everything we need to implement the self-hosted compiler, I didn't know that I actually need local variables. The more I implement the compiler, the more I realize what kind of features I'm missing. And if I'm missing a particular feature, I'm going to start a stream and implement that feature on the stream. So I already described that process, but I just want to reiterate. Right. So I'm going to continue re-implementing Porth in itself. And if I encounter something else that I desperately need and it will make my life easier implementing that compiler, then I'll make another Porth stream. We're going to implement that feature, and I'm going to continue re-implementing the Porth in itself. And once we implement it in itself, we're going to call it a victory, right? So I'm really looking forward to that, because at that point, I'll be able to finally lift my curse and not be a Python programmer anymore. So yeah. Basically, me programming in Python for several months already is a curse. And to lift that curse, I need to re-implement Porth in itself. Once I manage to implement it in itself, that's it. I'm not a Python programmer anymore. I'm free. I can do whatever I want. But until then, I'm forced to program in Python, and there's nothing I can do about that. Yes. Anyway, that's it for today. Thanks, everyone, and see you all next time. Love you.